This session is going to be talking about the future of materials, and you'll have an opportunity to hear program directors and fellows within ARPA-E and what our thoughts are in this space and what type of opportunities we may be thinking about. But before we get into that specific discussion about materials, I'd like to take a little bit of time and talk about how ARPA-E thinks about various problems in the energy space. And as you heard today in the introductory remarks, that ARPA-E, when they think about a problem, number one, a problem has to be transformational, something transformational that goes from not quite basic science, but comes out of a basic science idea, and we can move it towards commercialization. And what sort of impact will it have on the market if we do take that idea and move it towards a more practical implementation and commercialization? Well, then it should be transformative. And so ARPA-E is always looking for, we would say, transformational and disruptive problems in the market. So any problem that we take a look at, it has to follow the ARPA-E mission. And there's basically three elements of the ARPA-E mission. One is reduce emissions, increase energy efficiency, and reduce energy imports. And those are basically the three elements that we look for. Recently we had an open solicitation for projects, and we had close to 4,000 concept papers submitted to this open solicitation. Of those, 66 projects were selected for funding, and they span a wide, very broad range of topics within the energy area. What's interesting about these open solicitations is many times there's ideas that come out of these that seed new directed programs that we fund. And so taking a look at targeted programs or thematic programs, we have a number of them in different sectors that cover transportation to stationary power. And where do these focus programs come from, and how do they get developed? Well, what happens is, number one, we have sessions as this one where people come in and are open to feed ideas, or individuals within ARPA-E have an idea, and those ideas are debated internally significantly, and we ask questions of what sort of impact will they have? Are the ideas transformational? And will they be disruptive to the marketplace? Will they make a difference? And to answer those types of questions, we host a workshop, and we invite experts from around the country to participate in the workshops. We collect information and we get different perspectives. If we feel that there's sufficient motivation to move forward with the program, a certain program director will take that idea up, pitch it internally, and it goes through significant review internally to decide whether it can become a program or not. Once it's decided internally it's a program, things move very fast. The FOA is released, concept papers are solicited, respondees submit full applications, final selections are made, and contracting begins within less than a year. And when we take a look internally at various programs, we ask a set of very specific questions, and a lot of those go to the impact. Well, if we fund this, how long is it going to take to move that technology towards market? How much funding is it going to take to move that technology to market? What are the new approaches? So one of the things that I think the research community still doesn't understand very well is that a successful ARPA-E project that's funded looks very different than a typical NSF project that's funded. An ARPA-E project has to have a significant amount of transformation associated with it, and it also has to be a technology that can be moved towards commercialization. And we're very focused on moving technologies towards commercialization. And with that, I'm going to introduce you now to the next session, which is the future of materials. And you'll have 4 program directors basically talking about various ideas internally that we're talking about within ARPA-E. Please don't ask questions about whether a FOA or a program will be put into practice, because we're not allowed to answer those questions. So I'm going to start off the first pitch. I'm James Klausner, a program director, and talking about metals and manufacturing. My colleague John Lemmon will be talking about fuel cells. My other colleague, who's an ARPA-E fellow, Liz Santori, will be talking about materials for buildings. And my colleague Amul Tevar, who's also a fellow, and will be leaving ARPA-E fairly soon because his rotation is up and is looking for interesting opportunities. We'll be talking about materials for water and energy. Rather than soliciting questions from the audience, we're going to have a question and answer session. The questions you can text in, you can tweet in, or you can send in over the web. And the text, tweets, and web sites are listed there. So if you have questions, please send them in, and we'll try and answer all of your questions. So let's talk about metals and how it relates to energy. So one of the first things we recognize is that the production of metals and extraction of metals from ore consumes a considerable amount of energy. And worldwide, look at ferrous and some non-ferrous metals, it adds up to 21 quads of energy annually. So production of metals is a very energy-intensive endeavor. If we look at the various metals and how much energy is required to produce those metals, we see that three particular metals stand out: aluminum, magnesium, and titanium. These are very interesting metals because they have a very high strength to weight ratio, and we consider them as light metals, and are very useful for not only renewable technologies but also lightweighting of vehicles as well. But we see that the amount of energy to extract them are orders of magnitude greater than the theoretical minimum that would be otherwise required. There's tremendous amount of emissions associated with the extraction of those metals, and there's a lot of room to do a much more efficient job than we currently do in the production of these metals. If we look at the aluminum production within the United States, you see some interesting trends. One is that aluminum production is on significant and steady decline. One of the reasons for that is the amount of energy that's required to extract the metal and the cost of electricity relative to the cost of aluminum on the global market. And so what we see is the United States production of aluminum is not competitive. And so in order to meet our demand, we're at this point importing over 50% of our aluminum to meet local demand. We also see at the same time the demand for aluminum is rapidly on the increase worldwide. If you look particularly at the Pacific Northwest, that cents per kilowatt hour is the amount of energy that's required that the aluminum smelter would need in order to be competitive. And so the most competitive smelters are the ones to the left, the least competitive are ones to the right. And we see that from 2005 to current, we have 7 smelters that have basically been shut down and are no longer in production. So we only have 2 of those 9 smelters left in the Pacific Northwest. A large part of that is the cost of energy, because energy makes up about 25% of the cost of reducing alumina to aluminum. Also, the production of alumina has a significant energy cost as well, taking bauxite to alumina. What we see on the horizon is by 2025 we need to meet a miles per gallon standard of 54 miles per gallon for our fleet of vehicles, and any type of scenario you look at to get there involves lightweighting of vehicles. And the automotive manufacturers at this time tell us lightweighting is happening, which means there's going to be a significant increase in the demand for aluminum magnesium alloys or aluminum and magnesium. The problem with this whole paradigm that we see on the horizon is that if you calculate the total savings in energy from vehicle lightweighting, it's on the order of 2.5 to 3 quads per year. However, if you calculate the embedded energy required to extract the metal to do the lightweighting, it comes out to be about 2 to 3 quads per year based on your assumptions. So essentially we're just taking the energy and shifting it from fuel to producing the metal, and we're getting very little gain out of that. So we're looking at trying to be much more efficient in the way we manufacture our metals to actually get a net gain over the lifetime of the vehicle. Same thing is happening in aircraft. We're going towards lightweighting aircraft. There's a problem between aluminum and carbon fiber, which is used for the lightweighting of the aircraft, in that there's galvanic corrosion. So they replace aluminum with titanium. So we see a significant demand. The demand for titanium is going to more than double, even triple in the United States, based on the projection of new lightweighted aircraft that are being produced. Yet we have this problem of, number one, the high cost of extracting titanium from ore, as well as the energy embedded in the titanium. So based on these, we see a significant need to develop transformative technologies and rethink the way that we're making these metals, and we're looking for, are there new technological approaches to make these metals that are more efficient, more cost effective, that can help us be more competitive. Thank you very much, and now I'm going to turn the podium over to my colleague John Lemmon, who will talk about fuel cells.
Okay, good afternoon. Thanks, James. So I'm John Lemmon, and I'm going to give you kind of what I think is the ARPA-E view of how we think materials, new materials for fuel cells would play out, perhaps even some of the application space that we think they could play in. So for those of you who aren't familiar with fuel cells, these are electrochemical devices that are very efficient and probably a very green way to take fuels and make energy, make electrical energy. And you can see from the, our keynote speaker that this is generating energy in a clean manner. Reduced emissions is a very important thing for the next future. So if we look at, my title is More Than Efficiency Just Needed. Well, why do I say that? So fuel cells have been in the news for quite a long time. So if we look at automakers and alliance to speed up fuel cell development this year, LA show, fuel cells finally ready for the masses, 2007. Investors bet the fuel cells will become trendy again, 2002. So what's up? Here we have a very nice technology, efficient, clean, but still it hasn't made it to a massive commercial market. There are some companies that have more of low market volume things, but really to get to a broadened market, they haven't been there. So is efficiency enough? Let's look at this next slide. So the current focus, if we look at where fuel cell technology has been in the last current focus, and we look as a function of temperature, we can see that we have high temperature solid oxide fuel cell. You know, at this temperature, there's some benefits to run a fuel cell at these high temperatures in power density, fuel flexibility. However, there's some other challenging, really challenging things called, you know, degradation, thermal cycling, and being a ceramic, there's some manufacturing challenges. If we look at the lower side, and this is where another area that has been focused in recent years, is proton exchange membrane. This is low temperature. Benefits here include cyclability, simpler materials integration, and manufacturing because you're using a polymer membrane. However, these have other issues: hydrogen only, need for expensive catalysts, and also a high balance of plant cost because of humidification reasons. So, and also because of the hydrogen only and without the lack of a hydrogen infrastructure, these have been difficult to move forward also. So there's a gap here, and there has been some players in this gap. I'm not saying it's a complete white space, but it's an untapped white space. Intermediate temperature. And so our vision here is that could this be an area where you can combine the high and low temperature benefits and be able to do rampable fuel cells, so attain high ramp rates, use hydrocarbon fuels, especially in the advent of methane, our methane increase in methane, and can you get a cheaper balance of plant, and can we go to, because we're using high temperature, can we go to either no platinum or low catalyst loading? So I mentioned this is not like a wide open white space. There has been some players in here, and there's been the fuel cell community that tries to go down to low temperature fuel cells, and then you can see them here on the left. Those are some of the materials. There's been high temperature polymer people who've gone and developed new high temperature polymers, and you can see those on the right. And then there's been a few smatterings in this intermediate proton conducting area, some of these composite ideas, and certainly the solid acid type fuel cells. But by far, this space is pretty untapped as far as a white space in fuel cell materials. So thinking about the markets, generally we can think about energy in two areas, right? Stationary and transportation. Traditionally, if we look on the left here, the coal, stationary electricity, which is a growing market, and you saw the talk of the impact of electricity by the keynote speaker, and we look at a coal base load. Typical traditional is coal or natural gas base load. You have excess spinning reserve to deal with peaks. Now we're moving to renewable penetrations, and it requires more ramping, it's more distributed, and that's kind of a smart grid approach. Some of the emerging solutions, of course, are this grid scale energy storage, which we actually have funded a number of ideas in this. And also to take care of fast ramping, people are coming up with these fast ramping gas turbine to deal with the high peaks, the high ramps because of renewables. If we think about transportation, traditionally we're on an ICE, internal combustion engine, and now we're transforming to advanced ICEs, hybrids, plug-in hybrids, and now natural gas vehicles. And so if we look at a natural gas vehicle today, you're looking at reducing the range from 420 to 250 miles. One of the things here is that the MOVE program is trying to come up, and you've heard Cheryl talk about this in the introduction. How do you actually increase the amount of natural gas you can store for transportation? So how do we view this as where can fuel cells enable some of this new technology? In stationary, can we move from a fuel cell based load to a load following? Can we reduce spinning reserves? Can a fuel cell actually turn on and off and be able to ramp up high to reduce the spinning reserve requirements? Its ability to generate electricity and hydrogen for storage, and also this idea of trigeneration. In transportation, if we look across this, replace the ICE engines in a natural gas vehicle, we can get an increase in efficiency, and which translates to the bigger range. And actually, if we move to a higher temperature in a fuel cell system in a vehicle, we can enable a whole new class of hydrogen storage. One being magnesium hydride, if you can see the energy difference there. Instead of being stuck at 100 degrees C, where we have to live with lanthanum nickel 5 or tougher. So that's kind of where I'm thinking about fuel cells for materials, but it's what I'd really like the audience and you guys to think about is even more different electrochemical concepts for creating energy, or taking electricity, making fuels, or taking fuels and creating electricity. So can there be integrated fuel cells with storage, electrochemical regeneration of catalysts, as shown in this one, hybrid systems, alternative fuels? You know, what are your ideas? We're looking for out-of-the-box thinking. So come to the open networking session, and I really would enjoy talking with you. So thank you for listening, and I'll introduce the next speaker is Dr. Liz Santori, and she's going to talk to you about buildings.
Thanks, John. Good afternoon. My name is Liz Santori, and I'm a fellow at ARPA-E. And today I'd just like to convey to you some of the opportunities for leveraging advances in materials science to increase the rate of retrofit in buildings and rapidly decrease the energy use in the building sector. So as many of you know, buildings consume a significant proportion of the U.S.'s energy, amounting to 40 of the 100 quads of primary energy consumed in the U.S. annually. Of these 40 quads, 12 are used to heat and cool our buildings due to inefficiencies of the building envelope itself. So conduction through the envelope, leaks in the envelope, and solar heat gains through the windows amount to needing these 12 quads to moderate the temperature of our buildings. There are a lot of existing technologies on the market that can be implemented and that are more efficient than ones that are currently in today's building stock. However, they have not seen significant penetration in the building stock due to the low rate of retrofit of buildings and the long lifetime of buildings, given that they are infrastructure in this country. So just as a case example, the average vintage of a U.S. building is something like a 1972 Ford Ranchero, just because the average age of, or the median lifetime for a building can be upwards of 65 years. Looking at a component technology, windows have the average efficiency of a 1951 Ford Tudor with a fuel economy of 13 miles per gallon. 40 to 50% of the windows in U.S. buildings today are still single pane windows, so the least efficient, oldest technology you can think of, even though there are more efficient technologies on the market today ready to be implemented. So the question is, in the U.S., should we be focusing on new, more efficient technologies to increase the efficiency of our stock, or should we be focusing on technologies that can be rapidly implemented and see quick penetration in the building sector? So one possible strategy to increasing the rate of retrofit is a fairly simple idea, where you just maintain the component of the building, the infrastructure of the building, and just add to it to gain efficiency. So this would be as simple as applying a film to a window to increase its insulating properties. We know that aerogels are the most highly insulating materials known, and they can be made to be transparent. However, silica aerogels are very brittle and difficult to manufacture and will be difficult to scale on the sizes we need. So you might want to think about moving to polymer aerogels. So aerogels, very low density materials that are entirely made out of polymers or carbon. Currently, we can make flexible polymer aerogels, but they are not transparent. So the real challenge is, for the windows, how do we make these materials transparent so you can readily apply them to a window and possibly see immediate energy savings just because of the lower cost of conserved energy of this component. Employing such a technology could improve the efficiency of windows by 3x, resulting in 2 quads of energy savings. Dynamic windows, windows that can modulate the transmission of solar energy into a building, can have the potential to have a great impact on the U.S.'s energy use, both just energy use in total, but also reducing the peak cooling load of buildings. However, as we move forward and more energy efficient windows reach penetration in buildings such as low emissivity windows, we're sort of facing a moving target. You sort of don't want to replace an efficient window with a dynamic efficient window. Your energy savings are not as great. So I think we want to start thinking about retrofit opportunities for low emissivity windows that are starting to see significant penetration in the market. So one possible solution to have a retrofit film that's dynamic that you could put on the interior of the window is to just make it near IR reflecting. So one of the, not the issues, but one of the undesirable properties of dynamic windows today is they're primarily an absorptive technology. So if you put an absorptive dynamic film on the interior surface of the glass, it will absorb radiation, re-emit it into the room, and a lot of it won't be able to be re-emitted out because you'll have a low emissivity coating on your window. So you want to think about, are there technologies that can selectively reflect near IR without reflecting the visible, which would be aesthetically unpleasing? If we had such a technology, you could have daylighting savings and also reductions in peak cooling load by modulating the near IR. So that's one interesting solution that could be out there. So I've just sort of touched upon windows, but there are all sorts of inefficiency losses in the building envelope that are interesting to explore, and I welcome your questions via email or at the summit. And I'll pass it on to Amul Tevar, who is talking about energy and water and material solutions. Thank you.
All right, thanks everyone for coming today. My name is Amul Tevar. I'll try to move quickly to not hold you too long when I talk about the future of materials in energy and water. So I think that water will probably be the biggest issue for energy in the future, and that's primarily because of a global issue that's occurring recently with scarcity. This plot shows the United States with large parts of it undergoing what's called water stress. Depending on the data that you look at, if you look at the U.S. Drought Monitor, for example, in the Midwest, where I'm from here, you'll see areas that are undergoing exceptional drought, never before seen levels of drought. The issue becomes more complicated when you look at the fact that a lot of our population densities are along areas that already are undergoing significant water stress. Most of our water right now, about a third of our fresh water is used for irrigation, a third is used for power plant cooling, and a third is used for everything else. The reason that it's so important for energy is that our fundamental grid design was made with the assumption that water would be available and that water is the ideal cooling mechanism. There's new problems that have never occurred before. There's areas in the Northeast which have a significant amount of surface water. Power plants that are actually shutting down. A nuclear power plant actually shut down a reactor not because they didn't have enough water available, but because they didn't have enough water available that was at the right temperature. So there's completely new paradigms that are occurring because of the fact that the change is occurring very rapidly. And as we look into the future, we're expecting to have more power for more people, but we're going to have less water to do with globally. So the role of materials I see in this is there a way to make a water energy problem a materials energy problem? Are there changes, for example, to the incandescent light bulb through materials advances that make it LED light bulb, that make it very efficient, that make it use less energy and therefore use less water? So I'll be touching on two topics briefly, distributed treatment plants for water and water pricing. So 3D printing is a very exciting technology. Everyone's been hearing a lot about it. You can make these incredible shapes. It's not just limited to plastic, however. You can also make metal components that fully conform to ASTM standards off the press, excellent microstructure. And its relationship to water is, as we're thinking about this, is there a way to actually create and print out entire factories? For a lot of our produced water for natural gas, for example, there's either the water shipped to a central location for processing, or it's processed, it's trucked out and processed at another site. Can we actually use new materials innovations to allow stop-start 3D printing? Could you actually do a multiple material system where you actually build yourself a factory either on-site or make very cheap factories and then bring them on-site? And yes, you will pay a little bit more upfront for this material cost. You're essentially putting on a powder, you use a laser to draw a pattern, and you repeat this. And that initial powder is much more expensive than a comparative sheet metal. But the advantage would be that your final product cost, because it's essentially hopefully a one-step process, your final product cost might bring it down by an order of magnitude. So what are the materials advances that could allow this to happen? What kind of changes would we need to allow us to actually print on-site treatment factories for water? And something else that I think would have to be mentioned for any kind of water talk is the value of water. In the United States and globally, water has been tremendously undervalued because we've never really had these kinds of problems before. To enable any kind of water pricing or water valuation, you have to actually be able to count what you have before you can try to sell this. And this is a major problem with trying to come up with any kind of distributed network or system for accounting for how much water that we have in the United States. Regardless of whether from the Southwest or from the Northeast, globally, but even nationally, people don't know very well, to a good degree of detail, how much water we actually have and what are the kind of changes they're experiencing. And so I think there's a humongous set of opportunities within this sector as well for sensor systems. How would you power sensors? How would they communicate? How would you enable these sensors to adhere to different water systems and water pipes? So I think there's a tremendous number of opportunities, and I think we at ARPA-E realize it's a very, very complex space. There's interplay between regulations, water rights, but the fact is you have most of your power plants with a 30 to 40 year design span, and you have water shifts that are occurring within a period of 3 to 5 years. What is going to answer that gap? And I think there's a big opportunity here for materials, whether it be air-cooled condensers, water treatment plants, improving sensors. There's a significant opportunity for the future of materials within the water energy nexus. So with that, I'd close up, and anyone that's interested in following up with me, please find me at the networking session. I think we'll go right to questions.
So I think the organizers of this session overestimated your tech savviness and willingness to tweet in and text in questions. We did get one question, though. So the question that was sent in was, well, what about recycling of aluminum in light-weighted vehicles? Wouldn't that eliminate the energy embedded energy problem from primary metal? The answer to that question is absolutely it would. The challenge that is posed is right now we export probably about 60% of our light metal is exported to China or India. A large part of that is the valuable metal is the metal that has a low iron and low copper content. So if we were able to have sortation technologies that could discriminate between the valuable metal that has a low iron, low copper content versus the not so valuable metal that has high iron, high copper, we'd be able to keep that metal domestically, and it would greatly enable the economics of recycling locally. So one of the things we are interested in is innovative sortation technologies that can make that scrap metal more valuable and separate out the high value content of the metal. I think...
Yeah, we got a second question here, James, was maybe you could click backwards and put the address information for sending the text or the tweet. And then since the initial kickoff of the summit ran behind schedule, I guess since we're not getting any questions technically, we can go ahead and take a few here. Yeah, certainly. I think if you want to have a question...
Yell it out and I'll repeat it here.
What was the second question?
Could you put the address back up? Yeah, that's a very good question. So the question is centered around fuel cells and their role kind of in grid storage. So traditionally, SECA program focused on coal-fired gas plant fuel cell, and it's an efficiency play. You get a boost in efficiency with the fuel cell combined cycle coal-fired gas plant. So is what we wanted to look at is fuel cells in a different, and just let me back up. The other thing is that those things are not, you don't want to thermally cycle those. You're right. You just want to turn them on and let them run. Okay, so we don't want to go in that space. We want to look at new spaces in the grid where fuel cells could have an application. So and this is why we're having this discussion is on applications is, one thought is, can you use a fuel cell to replace, say, spinning reserves? Can you actually thermally cycle it, turn it on and off, ramp it up fast? Because right now, there's these spinning reserves you can't just turn on a gas turbine and have electricity come out of it. Of course, this competes with a lot of energy storage, right? But let's let the best, you have a horse race, let the best one do the best application. So that's kind of where I was pointing with that.
Well, I think titanium is an interesting element to deal with. regarding catalysts, I don't have specific idea on catalysts. I think that if you look at the industry as a whole, I think one of the opportunities are that you're operating at very high temperature. And built into the process is energy losses built into the process in order to protect the cells in which they're operating. So thermal management in these processes is really non-existent. And so there's a really big opportunity to do a much better job with the thermal loads associated with these and be able to reuse that energy rather than just dumping it out. So I think that's one opportunity. Another opportunity is just different pathways that we take. If you look at the parameter space on how you could actually do these from a chemical pathway point of view or from a physics point of view, there's really many different options. And I think what we're looking for is some creativity, trying to think outside the box of the standard way that we've been doing these processes for aluminum over 100 years. And I'll give you an example. If you use carbothermic reforming for aluminum, you could just right there reduce the theoretical energy by 30% just by using carbothermic. Now, that has its challenges, but why not? Can we get over those technical barriers, and do we have the technology to do that? Carbothermic is using carbon to react with the oxide, and the oxygen is pulled away from the oxide to give you metal. Yes?
My question has two parts, and I apologize, my hair is still blonde. Will you consider issuing an open solicitation for renewable chemical and advanced material platform technologies to compete competitively? There are some platform technologies that can be transformative across different specific applications and missions of ARPA, and yet these technologies seem to be master child, if you will, within DOE and USDA and Commerce. Yet they have considerable return on investment for taxpayers and want to.
So let me give you the short answer, is that number one, we're not allowed to talk about what programs we're going to fund in the future.
Great.
If you think you have an idea that's germane to the ARPA-E mission and that ARPA-E should be supporting, you're welcome to talk to any of the internal staff at ARPA-E and make your pitch and tell us why we should be funding it and why it's transformative and disruptive.
Okay, great. Thank you. And the second part would be, who specifically should we speak to here at the conference, other than Eric Toon and others who have already heard the suggestion? Who among the materials program division would be most relevant to talk about renewable chemistry and advanced materials, please?
So I think on this we just did close an open FOA. So with the open FOA, that was an opportunity where we provided no direction for where the program would take. And in terms of a specific opportunity, I think you can find any one of us and we'll try to get to the right person.
Thank you.
So we do have a number of questions that came in, and this one is for Liz. What are the best performing window films that you personally may have experience with?
Personal experience, I know my parents' house just has single pane windows and they have made no attempts to retrofit. So I have personal experience in this problem, even though it would benefit them financially to upgrade their windows. But I do know there are low emissivity films that can take single pane windows and add change their U factor such that they're closer to dual pane windows, but there's studies out there on such window films. But taking it to the next step would be if you could have an aerogel-like film, it would take it beyond those films today, which put a low emissivity, effectively put some part of a low emissivity coating on a window through a film.
So,
But I'm sure there's a huge space, so there could be other technologies as well.
any interest in hydroxide or anion exchange membranes?
Yeah, certainly. Certainly. That falls in the category of other concept slides, definitely.
For Amul, what about desalination and water supply?
I think desal is interesting. I think for water energy, one of the biggest things right now is what would you use. Desal is important for the United States. I think it's more important to what would you use to cool your power plants, especially as the water starts running out, over desal.
What role will standards and certification play within advanced materials getting to commercialization? Well, I can talk about primary metals. Certainly, there are ASTM standards on primary metals. There's association, like Aluminum Association has their own standards. And certainly the manufacturers who manufacture rely on those standards for different grades of material. So those are important. In terms of certification, I'm not sure that in primary materials where you have it's a bulk commodity that would be so important. Anyone else want to address that?
Yeah, I think just with what James talked about, certainly there would have to be some standardization and certification of how, purity of whatever materials you're making as far as metals.
Here's another one for Liz. A focus on retrofit technologies may make sense in the U.S. given the existing building stock. What makes more sense from a global perspective?
Yeah, certainly from the U.S. perspective, also focusing on a retrofit market is important for the U.S. That's ARPA-E's mission globally. Of course, you do want to focus on new technologies as countries are building their infrastructure. So taking a global perspective, yeah, you want to focus on new technologies and bringing their costs down.
John, for fuel cells, are you thinking more about materials or systems?
Yeah, at this point, I'm thinking about materials that can reduce systems cost. So reducing the balance of plant and manufacturing and things like that.
Guess this one for me is, how does energy requirements for manufacturing lightweight composites for auto industry compare to aluminum? Interesting question. Again, using lightweight composites such as carbon fiber, they're not compatible with aluminum, so you'd have to go to a frame that was titanium, and it just doesn't seem to be economical at this point. So I don't think that would be happening anytime in the near term. Certainly near-term aluminum magnesium alloys seem to be making the most sense for vehicle lightweighting at this time.
There's a gentleman in the back.
Yes.
I'd like to thank you guys for doing what you do and good presentations. I was wondering if, and I guess this would go for all the seminars, but if the information we saw up on the screen is going to be available on websites, and so.
Yeah, I think if you signed up for the summit, I think everything gets available by March 4th as a video cast. But
Yeah, also, some of these ideas we're thinking about, we've already held workshops on. And so if you go to the ARPA-E website and look under workshops, you can see much more extensive discussion and presentations on these particular ideas. Yes?
Cells. No, thank you. Regarding fuel cells, I was wondering if how progress is going with catalysts, platinum catalysts, mixed metal oxides. Trying to get rid of the high-priced metal content. Is that coming along, or what's your view of that?
Well, I think traditionally, much of the catalyst work has been done on the polymer side, obviously, through the EERE. Vehicle Technology Fuel Cell Program, and they've done a if you look across the board from 10, 20 years ago, they'd done a great job in reducing the amount of catalyst in there. There's still some ways to go, but, in the space I would like, in the material space I'm interested is do you actually need a catalyst? Can we run at a higher temperature? Can you run a hydroxyl or an oxygen conductor where you don't need a proton catalyst? So that's my answer to that.
So I think we have a question here. I think we're going to have to make this the last question because I'm told we need to wrap up because we have another session behind this one.
Just one quick comment. First, I tried using the web address, and it redirected too many times from my browser, so you may be losing some questions for that reason. Specifically for the idea of 3D printing or on-site constructing water treatment plants, is that the issue, or do we really need better technologies for treatment before we start thinking about how we're going to replicate them somewhere with a 3D printer?
It's a great question. I don't think there's going to be any single, within water energy, I don't think there's going to be any single issue that's going to be able to stand completely on its own because it's so complex. I think it's an important play that if we can keep the final product cost, if you look at the cost for essentially superstructure runaway, where how quickly does the raw material cost to the final product cost separate? The idea with the 3D printing is that if you can pay a little bit more upfront, yes, you would reduce the machining cost. But I mean, I think with the water energy, it's not entirely clear exactly where the perfect play would be. And that's, if you have any input on that, please let us know.
Well, thank you very much for your attention, and we wrap up the session, and we'll be around to talk with you more about these. Thank you.